Am I audible?
Yes, sir, you are.
Yeah,
Okay.
Karthik, very good morning.
Good morning, sir.
Morning. Yeah, so we can wait 5 more minutes. So because the participants are joining, so then she may introduce you, and then we can start the session.
Sure, sure.
Very good morning, all the participants and our respected speaker. So, since it is time for our session to be starting, I'd like to start today's session by introducing our speaker to all our dear participants. First of all, thank you all for joining us today. It is a pleasure to welcome our speaker, Mr. Prantik Sen, who is currently working as an applied scientist at Amazon, focusing on speech and audio understanding. He completed his master's in visual information processing and embedded systems from the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur. Please pardon me, there was some problem with my microphone. So to continue, his interests. Okay. His interest spans across speech and audio processing, pattern recognition, and computer vision, fields that are reshaping the future of intelligent systems. We are really grateful to have you here with us today, sir, for providing us with these amazing insights and taking time from your busy schedule to be here. Thank you once and for all. Thank you. I'd like to invite you to start your presentation for the today. Thank you, sir.
Thank you so much. Is my screen visible?
Yes, sir, it is.
Okay. So, good morning and a warm welcome to today's session on computer vision applications. We will be covering image classification and segmentation today. There are some hands-on sessions as well. We will start with some intuition from how the classical approaches used to be and how deep learning based approaches have taken motivation from these classical approaches. And like today, you know what the state of the art is like. Yeah, I mean, we are doing really great and exciting times ahead. So we will cover image classification right from some classical approaches to deep learning based approaches. We will move on to some hands-on session on classification then. After that, we will again come back for the next session on image segmentation, its types, the applications of image segmentation, and then again we will have some hands-on session on image segmentation. So that is what briefly we are going to cover in the next 2 hours. So what exactly is image classification? this should be the first question, and the answer is pretty simple. Given an image, you say that given an image and a discrete set of class labels, you say to which class label the image belongs to. So more specifically, let's say you have an image here, and you have a set of class labels which belongs to which is a set of animal names like dogs, cats, elephant, tigers, etc. You say that, okay, this image contains a cat. Now, let's go on to a mathematical formulation. So an image classification system is nothing but a function f, which takes as input an image I and gives you one or more class labels, depending on the type of image classification, if you are doing a single label classification or multi-class classification. And what is an image? It is a set of pixels. So if you have an RGB image, you have three channels, basically, red, green, and blue. If it is 8-bit quantized image, each of these can take up values from 0 to 255. Now, why is image classification so difficult, right? Now, going back to the previous slide, if you see, like, what appears a cat to us is nothing but a set of numbers for the computer. Okay, so how can we enable the computer to make sense out of these set of numbers, right? And this is not just an unique set of numbers. Like we cannot say that every cat will be represented by an unique set of numbers, right? Because there can be viewpoint variation. So this image is different from this image, even though they contain the same animal cat. There can be difference in illumination. Some images might be very bright, some images might be very dark, but then the object in that image might be the same, might belong to the same class. Then intra-class variation. As you see, there are cats of different colors, different textures on their body, yellowish, black, white, and so on. Background clutter, again, a very challenging problem in computer vision is to separate your foreground objects or the object of interest from the background, especially when there is this kind of a camouflage effect where your foreground object is very much similar to the background object, as you see in this image. And then occlusion, just part of the object of interest is visible and the rest is hidden. So having said all these things, can we come up with some representation, a kind of a common representation which can identify a cat, right? Set of handcrafted features, basically. If you have to do it like programmatically, if it is very difficult, but maybe till a certain extent we can. People have tried in the past, they have got some success, right? And what are handcrafted features? You take these features are basically like they capture some important visual cues, right? Like edges, textures, colors, shapes, corners. So if you have to imagine a cat, it has a very unique shape, texture on their body, the edges when you see an image. So possibly some sort of feature engineering we can do, but is that exhaustive? The answer is certainly no. Okay, so why this slide? I want you all to go back. If you want to pursue a career in computer vision, I would encourage all of you to go back, look into the classical computer vision literature. There are these concepts are really very interesting, how they have been developed. Some are very simple concepts, but yet very powerful. So how people pre-deep learning era, how people used to come up with these kind of handcrafted features like edge detections, corner and key point detections, texture detections, shape descriptors, and histogram of oriented gradients, Gabor filters. They have been in use like up until like not so long ago. Gabor filters were used for fingerprint identification. Like back during our master's days, we had implemented this to basically for fingerprint identification. Histogram of oriented gradients. Again, HOG plus SVM was the ImageNet winner prior to AlexNet. Right? So these are still very powerful features, but they have some limitations, right? They do not work, given a large set of diverse images, possibly they have limitations. They won't be able to give you features good enough. Now, moving on to the classical image processing pipeline. So what you have is an input image. You have some pre-processing steps. You do some brightness adjustments, some contrast enhancements, and then you input the image to this feature extraction pipeline, which can be one of these, right? Depending on the features you are trying to extract. If it is image classification task, maybe histogram of oriented gradients works well. So that can be one, and then you feed it to a classifier. It can be a support vector machine, k nearest neighbors, a very simple one, doesn't work very well. Decision trees or random forests, or even a multi-layer perceptron, few layers of MLP. And then the output is one or more of the class from a set of class labels. Now we discussed how this entire image classification pipeline can be basically formulated as a function, mathematical function f, which takes an input I, and then gives you a set of class labels, one or more class labels. So this entire step from pre-processing till the classifier can be considered to be that function f, right? Okay. Any questions till now? Okay, I will take that as a no, and I will move on. So now, what if we combine all the three blocks into a single one? Your pre-processing pipeline, your feature extraction pipeline, and your classification layer.
Sir, mostly questions are asked in the chat box. If you can
Oh,
please
is it?
just
Okay.
look into it.
Sure, sure. Okay, there are. Mathematical, okay, there is a question for images that contain mathematical plots. What features to consider? What kind of mathematical plots? Sorry?
Participants, you can unmute yourself to answer the questions.
Spectrograms. Spectrograms are nothing but your spectral features, right? You do short time Fourier transform, mostly used in audio speech kind of thing. So for spectrograms are features in itself. We do not explicitly do any feature pre-processing there. We can do some feature normalization there, but then they are features in itself. Does that answer your question?
Like I have like we can actually take a data into an image also, right? Instead of a long tensors format, we can actually
Mm-hmm.
take it into an image and process it, right?
Right.
So if we have, let's say, for simplicity, we have different types of standard signals,
Mm-hmm.
sinusoid or rectangular, ReLU.
Mm-hmm.
Suppose we have activation functions as in our images.
Mm-hmm.
So how does what type of features we need to extract? Like our filters are
Sorry, I think I lost you.
hello.
Yes, I lost you momentarily.
Okay, let's take an images of activation functions itself.
Mm-hmm.
Suppose we have different activation functions, we need to classify them. Some different graphs.
Mm-hmm.
Okay, so now what features are like we need to extract using the neural networks?
So you want to do some feature engineering before passing it to a neural network, right?
Yeah.
So in that case, good feature extractor to try out will be histogram of oriented gradients. If you see this slide, it captures edge directionality. So basically, each of your edges, like if you have a ReLU kind of a thing, it will have a different. It will have a unique direction of the edge. If you have, let's say, something like a sigmoid function, right? The edge directions will differ there. Sigmoid function is from 0 to 1. So this you can try with HOG, histogram of oriented gradients, and see if that works well.
Okay, sir.
The second question was, can you brief about pre-processing? Okay. Yeah, can you please elaborate what you want to know about pre-processing?
Yes, sir. Can you? Hello.
Yes, I can hear you.
Yes, sir. Actually, here my doubt is actually when we are handling with dental images, like when we go for fracture cases, do a dark image.
Mm-hmm.
When we go to dental images, there will be a grayscale like images. So
Right.
many fractures can happen when jaw region, for example, condyle region like that.
Mm-hmm.
So, if we are focusing on fracture cases, what are all the pre-processing steps we can follow? As you mentioned, like edges, all those things. So whether yes, we need there the edge technique to segment the region or remove the capture that exact fracture region, and we have to do some pre-processing. So whether we can apply these edges as a pre-processing over there to extract the fracture region exactly. Is
Yeah,
it
may not be ages, but something more, some sort of segmentation that we can do. If you have to get into this classical, like if you have to take something from the classical computer vision stuff, and we are going to cover that. So I can get back to you once we start on the session on segmentation.
what are all the other pre-processing steps?
Like what you can do here is you can try out some thresholding steps. So I am assuming that you are starting from an X-ray image of the dental fracture,
X-ray and images.
right? So in X-ray, like everything else becomes dark and your bones and all are white, right?
Yes, of course.
So yeah, so basically you can do some sort of, so very simple image processing from classical image processing literature technique would be to do some thresholding, and that thresholding can be adaptive. If your X-ray doesn't, like the brightness and the contrast changes across the image, you can apply some adaptive thresholding, or do a pre-processing. In the pre-processing step, do some contrast and brightness adjustments, and then apply a global threshold. And basically anything which you want to classify as your object of interest, that is that are the bones, that becomes white and the rest becomes dark. That kind of enhancement you can do.
Okay, so is pre-processing necessary for medical images?
Pre-processing in medical images, the thing is, training data is rare, right? So you usually, even if you have to go with the deep learning route, you get very less positive samples. Negative samples might still be abundant, but positive samples are less. So a lot of these techniques in medical images, not just because, two reasons why people for the longest time have been preferring classical approaches for medicine is, one thing is, it is a safety critical industry, and with deep learning you lack that control of what that model is going to predict, because out of distribution you never know. But this classical literature are very well mathematically formulated approaches on which you have control, first thing. Second thing is, due to lack of data, you never know whether the model you have trained is good or not. There are techniques to cater this data imbalance, but then still there is a chance that your model may not do well. For this reason, you usually do some pre-processing. You usually use handcrafted features, and still I can confidently say, because my friend is into medical research. He is a postdoctoral fellow currently, and he lot of the things he does is still like that still uses classical image processing approaches. So a lot of pre-processing steps goes into
For
that.
these cases, we are going for data augmentation, right? What you have said for lack of images, lack of training images, all those things, we are having data augmentation technique.
Data augmentation doesn't really always cater to, you do not have full freedom to do data augmentation in medical images still, right?
Hmm. So if we have, for example, if I have a real image of 100 images, can I
Mhm.
take it as 80 and 20 and I can go for training and testing, or I can go for that 80 for data augmentation and increase the level to get more accuracy?
You can do some sort of data augmentation, but then again, you need to see the images. And let me come to one slide. This will be interesting. So this is about pneumonia, right? Viral pneumonia, bacterial pneumonia, COVID-19 pneumonia, right? Let us say you do some data augmentation on the COVID-19 pneumonia and it starts looking like the one above, bacterial pneumonia. The class changes, right?
Yes.
So this is the challenge with data augmentation in a safety critical
You share
industry.
for the all.
Sorry?
It's not me, sir. Some people are.
Okay. Yeah, so this is the challenge with data augmentation in a safety critical industry.
Okay.
To some extent, yes, but again under a supervision of a qualified doctor.
Hmm.
And you need to see what the augmentation approaches you are using, what kind of output images it is giving,
Okay.
right? Because for a layman like me, bacterial and COVID-19 pneumonia, they're quite close to, visually they are quite close,
Yeah, of course. Hmm.
right?
Okay, sir. Thank you.
Yeah. Are there any questions? Any more questions?
Just one curiosity, like you mentioned in the one of the previous slides that about classical computer vision classifiers.
Mhm.
So are perceptrons also? You mentioned perceptrons also can be put. So are they also considered part of classical computer vision?
I mean, not computer vision,
Okay.
machine learning stack definitely. You use this as a classifier.
Fine.
Your
Okay, like
features are still handcrafted. That's why it's classical in pipeline.
all right. Yeah. And one quick question is the image augmentation you were talking about. Could you just, in maybe a couple of lines, tell, I mean, what does augmentation refer to here?
Yeah.
Like,
So basically, you do some sort of it is pre-processing. You do some, let's say this input image of a dog, right? If you crop this and just have the face of the dog without the background, it is still a dog. If you rotate this image vertically, it is still a dog, right? So from one image, you are generating two more images. So basically, you have three images, but the output is still a dog. So this will help the model generalize better when you train any model for that sake. It will help it generalize better.
Yeah. Okay. Thank you.
मेल मोकलो कि मेल मेरे को नहीं मोकलो है
Thank you.
Are there any more questions, or I think we can move ahead? Yeah. So now move on to CNNs, convolutional neural networks, which has been like ruling the last decade or like 12 years maybe, 12, 14 years, right from 2012 when AlexNet came in. So again, going back here, we'll see how this three blocks are captured here. So basically from an input image, these CNN layers, convolutional kernels, they capture your features, right? And finally, you flatten out the features, and then you have a fully connected layer. The perceptron, which we were talking about, that is still the classifier here, right? So
Yeah.
feature extraction is being done by your CNN blocks, and classification head is this. Finally, you have a softmax activation. So there are multiple classes, and finally you get a probability distribution across the output labels. So building blocks, again, like you have convolutional layers, you have some non-linearity, which is ReLU activation here, and you have some pooling, which basically decreases the spatial resolution of the activation maps at each step. So if you see this, the left image is the bigger one, and then as you move deeper into the network, the spatial resolution decreases, the depth increases, which is nothing but the features. Is there any question on this? I think most of you are familiar with this. So like intuitively, what this convolutional neural network is doing is, in the feature space, if you have to plot and visualize the feature space, again, that is a very high dimensional space. It is very difficult to visualize in that high dimensional space, but you can use something like t-SNE visualization, which maps your data points from a high dimensional space to 2 or 3 dimensional subspace, and then uniquely maps those data points. So you can still see um, how the data looks like in the vector space. Now, this is the MNIST data set, very, very common data set again. You have handwritten digits here from 0 to 9. And after a classifier has been trained, let's say for each of these images, you take the embedding. Embedding comes from a layer before the classification head. So you take the embedding, which is nothing but the features for that particular image, features which this classifier has learned. You use that features and you use t-SNE and project that to a lower dimensional space. So if you do that, a good classifier should give you something like this, where like objects belonging to or items belonging to the same class are closely packed and they are far apart from the other objects. So basically, if you see, the targets are digits from 0 to 9. So each of them are closely packed as depicted by the colors, unique colors used here. But then this pink one is far apart from blue one, or even the other colors, orange one. There are some basically overlapping clusters that you see here, and that is because of confusion in the handwritten digits. So from these 4 images, it is difficult to visualize, but there are occasions where, let's say, this 4 might get confused with a 7 or something like that. So overlapping things are because of, one reason is because we are projecting from a very high dimensional space from a low dimensional to a low dimensional space. So might be because of that. It might still be well separable in the high dimensional space, but another reason might be the confusion. If you visually look at it, there are confusing examples, and that might attribute to this overlapping subspace. And any question on this? Let me check. Yeah.
Hello.
Yes. How convert image directly to convolution layer? Is there any steps following to convert? Can you explain this question, please? How convert?
You have shown that zebra image, right?
Mhm.
Automatically you are showing next convolution layer. So it is in the format of images, whether how we are converting that image to any text format or value, something else, how that processing steps happening.
So in
Because
these
machine
kind,
can't understand directly as image, right? Or the image directly will read by convolution layer, or what are all the libraries or something else we can follow here.
so basically, if you see this, computer will take an image. What I mean is computer will be reading these set of numbers and processing on these numbers. Is that clear? So when you load an image using some library, it is nothing but a set of numbers or tensor, you can call it, a set of values in some array format. So that is what is happening here. When I say I am giving this image of a zebra as input to this CNN blocks, it is basically it is taking these values and doing a sliding window kind of thing using the kernels, convolutional kernels.
For make that values to be readable by the system, is there any thing we have to follow for that?
No. So there are libraries to load images.
Mm-hmm.
You just load images onto memory. If you want, we have some hands-on session. I can tell you in details there,
Okay.
maybe. Right?
So I also had a quick question. Could you, in the context of this particular representation, what is the role of this flattening layer, especially in this kind of application of computer vision?
I mean, so basically, at this point, what you have is the spatial resolution has been is a very small number, or maybe one, right? If it is one, you do not require a flattening layer. If this is one, this small spatial, is my pointer visible? Wait, let me use a pointer. Yeah, if this is one, and this is, let's say, 512 of them you have, then you do not need a flattening layer. You have 512 features coming from this image, right? And you can feed it directly to this. Otherwise, if there is some spatial resolution here, let's say 2 cross 2, and you have 512 of them, you just make it 512 cross 2 cross 2. And the significance is this flattening layer, this is not a fully convolutional network. So you have some MLPs, and that basically accepts inputs of the form of batch cross the feature dimension. So to have that feature dimension, input feature dimension, you flatten this out. Does that answer your question?
Yes, so kind of. Thank you.
Okay.
After this,
Yeah.
we are feeding these values to the neural network, sir.
This is also a neural network, convolutional neural network. This is a multi-layer perceptron. Again, another form of neural network.
Okay. So we are feeding it to convolution and then multi-layer perceptron.
Yes. You can as well, like before CNNs came in, what people used to do, they used to flatten these images. Like you have, let's say 28 cross 28, you make it into a single row vector, 28 cross 28, 784 dimensional vector, and you put that as input. That the same role this flattening layer is doing here.
Okay. So here the output has been given as 3 values: horse, zebra, dog, whether it is a multi-class classification or like a binary class.
This is not binary. So binary means you have two class levels, either 0 or 1, right? This is multi. You have you are predicting out of like 3 class levels here. 1 out of 3. Mostly.
Thank you.
Okay, so we will quickly go through evolution of image classification. Like pre-deep learning era, I already mentioned how the handcrafted features and then classifiers like SVM random forests were used. And this is how, basically, if you have a good feature extractor and you give it to a classifier, it should be able to draw a decision boundary between the two classes. Then AlexNet came up in 2012, and after that, like a lot of evolution happened. A lot of new networks came up. People tried to achieve high accuracy with less bulkier networks, less number of parameters. So all those things happened. A lot of evolution, like convex evolved all through like 2012 to 2020, and then like attention is the way forward. People, this is where like the state of the art lies, and like vision transformers is being widely employed today. Even though there are cognates have not yet like gone out of the scene, totally gone out of the scene. These two are extensively being used, both cognates and transformers. Okay, so we'll move on to applications like healthcare. So image classification, again, like if you are given X-ray images and you are asked to classify what kind of pneumonia, or is it a normal X-ray, normal lungs. Uh, Computer vision is widely used as a doctor's assist. Again, in safety critical industry, we still like AI still do not take the role of a medical practitioner, qualified medical practitioner. These are just used to assist a doctor to make a decision. Retail and e-commerce, yeah, we all do online shopping, and if you want to basically, let's say, search for a blue shoe from a catalog of available shoes, you can like upload an image of a shoe you want, and it returns you all the relevant data shoes from its database. Or you can just put some textual description like I want blue shoes with high heels, or sneaker kind of, and then it basically retrieves from its database. So how this works, you already have uploaded, like all the manufacturers or sellers have uploaded images of shoes, and then there is some image classification or some computer vision algorithm, mostly neural network based, CNN based, working in the background, which is capturing some features corresponding to that shoe and storing it somewhere. And then next, when you upload an image using the same pipeline, the embeddings are computed, and then there is some similarity search that happens, and then finally images which are similar are retrieved back as suggestions that these are the things you can look into, which are available on our website. Again, a very important application is computer vision based facial recognition, access control mechanisms like in offices or restricted areas. Basically, you have a camera and you go and stand in front of the camera. It captures your face, tries to retrieve with the, tries to check in the database if that face is already registered. If you are authorized to enter the premises, then you are given access. Otherwise, your access is entry is denied. And like this comes from like FaceNet. I will briefly talk about how that evolved. So basically, this is not a very simple kind of classification that happens, because a cats versus dogs classifier or a shoes, you are asking for a red shoe and a blue shoe is returned back as a suggestion. That is not as critical as a person who is getting an unauthorized entry to a highly secured premises, right? So for that, what you need to do here is, like, I might look similar to some other person. So how to distinguish between me and that person? So something called as triplet loss is used there. So basically you have an anchor image. So this is during training pipeline, you have an anchor image. So that is, let's say, my image. I have 4 more of my images, which are positive images. And then there are other images of other people, which are negative images. Now, my objective is, in the embedding space, I want to be as close as the embeddings of my images, but as far apart as possible from the embeddings of the other people in the database. So that is where the margin comes from. And the formulation beautifully ensures that this margin in the embedding space is maintained. So whenever, like after this model has been trained, whenever a new person comes, whenever you come, it will match with your image, and if there is a match, it will say that okay, this person is so and so, and you are allowed entry, or you are denied entry if there is no match. So now fault detection. So this is something which I have personally worked on. I took this image from this link. Uh, so for fault detection on solar panels. So basically, solar panels, if you have seen, like not the ones above on your terrace, but there are solar power plants where, like on a huge field, there are lots and lots of solar panels laid in rows. And then a very common problem with these solar panels is, like, let's say with time, with weather conditions. Let's say there is a hailstorm, some ice strikes this solar panel, and then it creates hot spots, and they are basically faulty. So they become very hot compared to the other regions of the solar panels. And this kind of detection is done using IR cameras, which capture the thermal profile of an images. So what I mean by thermal profile is, so if you read this, IR images are often colorized to enhance visual representation. Different color palettes are used, with warmer colors like red, orange, yellow representing warmer temperatures. So this is an IR image, okay? And human beings are usually like, your body temperature is warm when compared to the surroundings. So if you see, they are like captured in red here, and the other people are like in blue. The roads are in blue. This building walls are relatively cooler than the human being, so they are in yellow. So you capture this image, and then you can do some hotspot classification if you find. And by the way, these are done using geotagged images. What I mean by geotagged images is, you have a UAV which flies over these, and the images will have the geolocations, the latitude and longitude, so that after the model says that, okay, this image is faulty, you get the geolocation, latitude and longitude, you go to the exact place where the faulty solar panel lies, and you replace it. Uh, yeah, is there any question on this? So basically, this is how the faulty solar panels look like when you capture with an IR camera. These red regions and yellow regions are faulty regions, and you just have to replace the solar panel. Then there are fraud detections. So many variations of Bisleri and Adidas and Nike and Puma are available. So uh, yeah, basically, again, an application in retail. If some seller is registering their products and they click an image of that particular object, let's say a shoe, and you have this logo instead of the original authentic logo, then there are algorithms which can run in the background and mark them as fake and remove and delist them from their websites. So yeah, is there any questions till now? Because next we will go through a very interesting video. Let me check. Okay. No questions? Okay. So this is a video of a self-driving car. You can see the video, right?
Yes, sir, it is
Yes,
visible.
sir.
And the audio is also visible, right?
Yeah, we can hear the
Okay.
video's audio.
Good. So this started at IIT Kharagpur, and people, those founders have moved on to the Bay Area, and that startup has been acquired now, started by 3 people at IIT Kharagpur. And let's see this. This is a self-driving car, basically. Yeah. So I'll pause that briefly. Let me go a frame back. Yes. If you see this, there are these distinct red lines to mark the boundaries of the road, right? Then the roads are colored in the bottom image. I'm talking about this, the map, beside the map, right? The roads are colored in all in white, and then the surroundings are basically ignored. So some sort of classification, some sort of edge detection, like your edges, the road boundaries are being well defined. So some sort of edge detection is happening there. some sort of segmentation is happening here because your roads are getting segmented. And then also the cars are being detected and shown in the image, right? So a lot of computer vision stuffs. So you can imagine how much computer vision goes into a self-driving car. You see the road boundaries marked in red. Okay, let us take 2 minutes. Can can um, can you all identify what all things are happening here? What all in a self-driving car? What all things you need to take care of? Um, yeah, you can type also if you want to. Okay.
Participants can
Yeah.
unmute yourself too if you got to answer. You got the permissions.
All kinds of moving things around the vehicle. Yes. Vehicles, pedestrians. Yeah. Anything else?
So, like you mentioned, a lot of computer vision is happening, and first marking the boundaries of the road itself and creating the background, and also segmentation, like you said, segmenting it from the other stuff. And then on the road itself, whatever moving objects, like someone has already said. So, and then marking the dimensions of those objects. How big are those objects?
Mm-hmm.
So the size and dimensions and that boxing.
Mm-hmm.
These are some of the obvious things. Yes.
Yeah. Yeah. True. True. Thanks. Traffic lights, identifying they're green, red, or orange. Right?
Yeah, absolutely.
Yeah. Yeah. Yes. So we will start with simple things. So yeah, I hope you all are excited seeing this video. And let's come back to convolution.
Ryan,
So, sorry, is there?
yes, I have a question here.
Okay.
In this video, is there we have some limitation to cover that region of images. If the car is placed at one place, placed at the exact one location,
Mm-hmm.
the vision of the camera is showing at a particular region only. So we can do that more than region, or is it's a limitation of that camera whether it will be covered.
Well, there are 360-degree cameras also, and I think in this video, towards the end, they do.
When you show that last place of it covers the bridges on four sides, but one region will be getting right, some till some region it will be bright, and some of the region get it's not covered.
Okay, let's see.
So in picture you see.
Mm-hmm.
So here the region of coverage will be, is there any limitation in camera? Or we can, if we want to view more, is there any camera is available to fix it?
I mean, there are 360-degree cameras which can help you get the entire view. It can be mounted on top of the vehicle. But for driving per se, I think till, of
So
course,
then what my question here, you are doing this process inside the campus, so the limitation of driving is the kilometers will be less. When I'm moving in highway, if I'm in 140 or 160 kilometers,
Mm-hmm.
so suddenly any vehicle is coming, whether this process will capture of image, suddenly it happens. So this thing is possible.
Yeah,
Okay.
definitely there will be feedback from the, like what we do is we usually, before changing lanes, we see the rear camera, right? If any vehicle is coming on the, approaching on the other lane at a high speed from behind. So definitely those systems will also be there, I suppose.
Human, when we are driving for example, for 100 on 150 meters, if any vehicle is coming back, if I am sitting in my side mirror, I can able to identify whether this is able to cross us, or they can, based on the driving person, we can able to identify whether this person is going to turn right side or left side, and we are able to drive.
Mhm.
As a vehicle, whether it can able to identify.
Should be able to, because if you see here, you have a single road. There can be lane markers as well, right? That can be drawn here if it is a two-way road, and those lane markers can be used as assist to take a calculation. And basically, if you take a video of any object approaching you, either from front or behind, the scale of that object changes with time. If it is approaching you, if the scale of the object remains same with time, let's say you are driving a car, and the car behind, the shape is the same, the scale of the object, scale of the car behind on the mirror, when you see, if that is the same, which means both the vehicles are being driven at the same velocity, right? Same speed. Now, if that is changing, that means that is changing. And if that is increasing, basically from a small car, slowly, when you see in the mirror, the car becomes big. That means it is approaching you at a higher speed, right? So those kind of things can be used to take a decision in this case. Like how your brain thinks, your brain also thinks in a similar way,
Okay.
right?
Okay.
While taking decision. Does that answer your question?
Yes, sir. Of course.
Okay. Yeah. So we will move ahead to the next slide. We will come back to convolution. We have talked about all these applications, but what is convolution? Okay. So again, this portion is little bit, the motivation comes from classical image processing. And then we will see how this entire theory or this entire thing translates to our deep learning world today using convolutional neural networks, right? So given this image on the left, you clearly see there is a vertical edge. You have a gray left portion and a dark black right portion. And if you have to detect this vertical edge, how will you do that? And this image can be represented in an array, like your left has all these pixels marked as 70, intensity value of 70, and then you have all these as 0. So the small patch within this square boundary, right? So can we do something with some handcrafted features? So let us take this as a kernel. We talk about convolutional kernels, right? 3x3 kernel size. So let us assume that one of those convolutional filters is this, where we are not learning it, but we are explicitly setting its value. So the first column is all +1, the last column is all -1. And what we do, we slide it over this entire original image from left to right, then top to bottom. So if you do it through the entire image, you see you have two columns with zeros, all zeros. You have the rightmost two columns with all zeros. Center column has a higher intensity value, which is close to 255. So it will have a whitish kind of an appearance. And this is the output image, which is nothing but if you visualize it, it has been able to identify the vertical edge in this image. Now, this is in image processing literature. This kernel is called Privet filter or Privet kernel. Similarly, you can have a kernel.
Excuse me to interrupt you. Yeah, just could you just throw light on this actual computation, like why 210 only to mark
Okay.
the boundary between gray and black?
Okay, it comes from here. You have this, right? So basically what you are doing, plus 1 into 70, 0 into 70, minus 1 into 70, plus 1 into 70. So you do this, you get 0 for this. Take that kernel, put it in the middle, do the same computation, you will get 210.
All
Yeah.
right. So in that case, this particular kernel only will work, right?
To detect the vertical edges.
Yes. So how do we chance upon this particular kernel?
These are very well-defined kernels coming from classical image processing literature, right? And in CNNs, you randomly initialize these. When you say CNN filters, you randomly initialize these, and these are learned.
Okay.
When you define a convolution 2D with kernel sizes 3, strides of, your stride will determine, stride of 1 means it is shifting to the right by 1 and then to the bottom by 1. Stride determines that. Padding determines how much padding you are doing to the original image. If you want to, if your output image, you want to have the same size as the original image, or if you do not want that, you do not use any padding, so that your output image will be slightly smaller than the original image, those kind of things.
Yeah, those are all the options or choices we have to make. But just was wondering, if we had chosen any other 3x3 kernel, what would happen?
Yeah, I mean, you can you can possibly have a vertical edge detecting kernel. So vertical edge will be, you take transpose of this. So first row is all +1, then all 0. Second row, third row is all -1. You try to do the same thing, you will get a dark image. It will not give you anything because there are no vertical, horizontal edges in this image.
Oh, yes.
Right? So these comes from very classical image processing literature. In your CNN, these kernels are learned. When you say you have 64 filters, 3x3, you have 64 of these kind of kernels on the left, and then you are learning them as part of the training process. So they possibly one of them might have learned this exact thing or somewhat different, which is helping in detecting vertical edges. Something will help in detect horizontal edges, maybe edges at some orientation, 45 degrees, 60 degrees, all those kind of complex features you learn.
Okay, yeah. Thank you.
So again, we were talking about edge detection, and then there are a lot of vertical edges in this image. There are some images, lines at 45 degrees also, if you see this. Let me use the laser pointer. So all these, like, edge detection is a very simple problem, I would say, today when it comes to classical image processing. But then the motivation comes from there, like the motivation of using this kernels in CNNs comes from this exact thing. Only thing, we are learning those kernels. Here we have fixed kernels. And what is an edge? Edge is nothing but a sharp change in intensity. So if you see, you have an image patch here. You have a bright spot on the left, bright patch, and on the right as well, you have a dark patch here. So there is, from 255, the intensity suddenly drops to 0, and then again it goes back. So if you take the first derivative here you have a, here you are basically coming from 255 to 0. So you have you have a peak here, inverted peak, and then again when you are going from 0 to 255, you get another peak. So basically, you will get two vertical lines as edges here.
So, does it mean, sir, like the number of kernels would be more number of kernels would be required to detect edges, in a previous slide, because there are so many edges in those buildings. We earlier saw that in order to detect one vertical line, we needed one kernel. So, so the decision of the number of kernels, is it directly proportional to the number of edges?
I mean, in today's world, in deep learning world, we just give it a number like 64 and let the network learn what kind of kernels it wants to learn.
Okay,
But if
64 as the number of kernels?
64 as the number of kernels, and then we let the network learn whatever it has to learn from the data.
Mm-hmm.
Right. So, like again, very simple kernels, -1 and 1. If you do the same thing, -1 and 1, if you do it here, if you do it all the way till here, -1 and 1 means -70 plus 70, it will be 0. But here you will get some -70 plus 0, you will get some positive numbers. So basically, you are still able to detect the vertical edge. So these are, again, very simple filters. But if you take the derivatives with respect to x and y, these are the kernels you are going to use. And you see very different edges. This is more of vertical edges, which it is capturing. This is capturing the horizontal edges. Right? So we will move on to, if there are no questions, can number of kernels be more than 64 also? Yes, it can be more than 64. It is just a hyperparameter or a parameter of the network that we set. We will move on to some hands-on session if there are no more questions. What is the time? Yes, I think we should move there. So yeah. So we will start with a CNN, a simple CNN to do a cats versus dogs kind of a classification. And as the network is training, I'll show you some of these edge detection things that I was mentioning. Okay. Are the notebooks visible? Sure, I'll share all the collab. Okay. But it does. Can you check if you are able to access it, or how do I share it? Wait. Okay, it is restricted. Anyone with the link. Can you access this? Can someone please confirm? Okay. Yeah, someone has confirmed. Thank you. So let us quickly start with this. Okay. Connect without GPU. So first, Cell is like importing some basic libraries, Matplotlib, TensorFlow, and the image data generator. So then I'm downloading the data set, the cats versus dogs data set, and this is how the folder structure looks like. You have a folder with all cat images, and you have a folder with all dog images, right? And these are getting extracted at the moment. I'll hide this. Okay. So next, I am creating the training and validation data out of these images. I will use some of them as training images and the rest as validation images. So I will have another folder, cats and dogs, and I have a folder train within that cats and dogs. So basically, this image data generator, if you have a classification problem and you just point to this train and validation data set, it creates the data loader and data generator itself. Right, and it says it has found these many number of images in total belonging to cats and dogs, and then 5,000 images belonging to the validation set. Let us visualize. Trend gen is not defined. Trend data gen. Okay. Right. let us visualize some of the images. Yeah. So this is how a cat looks like, a dog looks like, and then we have this network, a simple CNN network. If you see this, so first I have 32 convolution kernels of 3 cross 3. We were mentioning 64. So we start with 32. Next, we have in the next block, we have 64 of these kernels, and then followed by 128. So if you see this image of a typical CNN, as you go deep, your number of filters increases, but the spatial resolution decreases, right? So this is how the network looks like. It accepts as input 126 cross 126 image, and then you have a max pooling, which basically with 2 cross 2 max pooling, if you see this, 2 cross 2. So basically it will reduce the spatial resolution to half. So you have 63 cross 63. You can do conv 2D, 64 of those filters we have. Then again max pooling, then again another conv max pooling. Then we are doing the flattening layer, and then 2 dense layer classification, basically heads. So similar to this, right? And let us put this for training. This I am not running on a GPU, so it will take time for me. If you have any questions, we can address those questions till it trains. Can everyone confirm if the training, sir, you can change it to GPU? Oh, my computes, I have exceeded that, so I am unable to do that.
Sir, just I had a question. You showed a certain architecture that that how many convolution layers you use, then the flattening and it. So just if you could throw light on how you arrived at this particular architecture only, and did you try various combinations and different alternatives, trial and error, and
No, this may not be the best network that works for this data set. I did not do an architecture search, just added some convolution max pooling blocks, the usual image processing, image classification pipeline using CNNs. Randomly added, got around, I think 87, not 87, 83% validation accuracy, but then you can try out different permutations of these things, add more filters and see if that helps.
So there can be self-attention block also, right?
Not in this, that needs transformers. But yes, you can do classification using transformers, vision transformers. So a few things to note here is, since there are two classes, cats and dogs, so we can treat this as a binary classification problem. So so your activation function at the final layer is a sigmoid. So sigmoid can take in values between 0 and 1. So it's a very nice probability distribution when you have a binary classification kind of problem. And for that, the loss function is binary cross entropy. If you have more than two classes, you can go with a softmax activation here, and then the loss will become categorical cross entropy loss. Is the training as for image? Okay, as for image processing, we have so many algorithms at present. Whenever we take any of the image and want to work for image, like cancer, are we supposed to first use CNN first? I would suggest, if you have a very good number of images, try with CNN first. And use a network which is small as possible. And since these are medical images, we may not get many images. So we can just do some sort of a transfer learning where you pick up a small network which has already been trained on other data sets. So it has already learned the feature extraction pipeline. What you might do is fine tune if you last few blocks, and then the classifier head can be fine tuned on your training data. Image processing, like usually in CNN, if you have a lot of data, we do not do any image processing, any classical image processing, pre-processing. But basic augmentation, you can do some sort of maybe contrast enhancement, brightness enhancement, and just visualize those, just see those images after those augmentation has been applied. It should not change it so much that it goes to a different class altogether. So your normal person should not become a person with some disease, and vice versa. Okay, is everyone able to run the notebook? Can you please confirm in the chat? Okay, as the training is running, let us move to this. I wanted to discuss the edge detection thing. Do some hands-on there, basically. Okay, completed training. What kind of accuracy are you seeing in the plot? 84, 85, maybe more. Okay, let that train. We will visit that later again. So let us see some classical image processing things. We were discussing about edge detection and all. So this is an image where the left portion of the image is all bright, 255 is the intensity value, and the right is all dark. So if you see how I created this image, I first initialize a 224 cross 224 images, all with zeros. So after this, if you visualize, it will all be a dark image. And then just till half of the columns, I am making it 25. So half of it becomes white, half of it becomes dark, right? And this is the private kernel that we discussed. So this is the kernel that we discussed, and we are going to use that kernel to do a convolution. So CV2 is again, like we are using this OpenCV library. I think someone had the question on what kind of libraries we can use. So OpenCV certainly is one of the very prominent computer vision library out there. So if you see, it has so nicely detected this vertical edge, which we were talking about sometime back in the slide. Right? There are other such kernels as well. This is another one which looks similar, but the center pixel is 2 here. So you are giving more weightage to the center pixel. So if you basically try to use this filter, you get a similar vertical edge. So this is the motivation behind today's what we have today as CNNs. We use a lot of such filters, and the kernels, the values inside this, like you have fixed values here, but these values are learned basically as you train. So as your training is happening here, one of this 3x3 kernel might have learned. You can visualize later. You can print those values and see what kind of features it is learning, but might have learned something similar. Yeah. So any question on this? Can you share the collab? Okay. Yeah, sure.
Sir, can you use roadmap or working with computer vision? What are all libraries we have to learn? Can you share the sources for learning?
Yeah, sure. I would still encourage you all to
EAL, that is
uh,
like so below, right? And CV2, all
yeah,
those.
OpenCV is one library. Then either you take PyTorch or TensorFlow, whatever you are comfortable with. Yeah, that should help you get started. I would you start from classification problem, try to train a network, use this notebook maybe, try different architectures and see how it works. And then I would also encourage you all to go through the classical literature and see how things worked back then and how some of the things, the motivation behind some of the things we have today just comes from the classical literature. The classical literature, why I appreciate so much is the mathematics behind it. People have thought so much, came up with simple features, yet they were decently powerful. Uh, Today, with CNNs and all, with deep networks, we lack that controllability. We do not know what the network is learning, but with classical approaches, we do know what exactly is going to happen. But having said that, SOTA is all CNN transformers based. We are in this deep learning era. So, yeah, start from classical and progress towards whatever is the SOTA today. And you can use these libraries to get started with.
So whether this OpenCV is enough, sir, or as I asked you before the doubt, how to convert that zebra to the vector values. For that, you said some of the libraries, right?
Yeah, OpenCV is enough. OpenCV CV2 dot. So OpenCV has got this.
So whether this OpenCV can
Yeah,
do
this is used to read
the
images.
vector, that is pixel value you have showed, right? Whether this CV can convert that image to that pixel value automatically.
Yeah, if you see this, I am doing some CV2 operation here. Let me print some values of this. You see this? All zeros for black. So these are all your vectors. Does that answer your question?
Yes, sir. Yes, sir.
So whatever you see visually has got a digital representation, which is nothing but numbers. Again, depends on whether you, what type of data, what kind of data type you're using, unsigned integer 8 or float 16. Otherwise, these are just numbers.
So
For the computer, these are
this value you have shown as a 0 will be taken to the system, right?
yes.
Okay.
If I print everything here, let's see. It is show data. So it is all zeros, if you see, and then there will be this center part where you will see 255. Maybe let me check if I can show you that 120 to 130 somewhere. Yeah, you see this. Okay, 125 to 27. You see this 255, right? This corresponds to this white patch. Rest all are black. So yeah, I think we should move on to segmentation. I still have a lot to cover. But yeah, so let us go through what segmentation is. So we till now we have covered what classification is. And classification is given an image, which class it belongs to. Now, what is segmentation? Segmentation is grouping meaningful pixels, grouping similar pixels into meaningful regions. So when in classification, you are saying that in this image I classify as a cat. Here, what I am saying is this pixel I classify as something, right? Pixel is the smallest building block of an image. So any data represented here, I am showing you the numbers. Each number corresponds to a pixel in the image, right? So basically, what do you see here? You see an image. What does computer see? It sees again a set of numbers, right? Now, what is the objective of image segmentation? Group similar pixels. You have a car, you have multiple cars, you are grouping them together, you are coloring them, all the colors with blue. You have multiple people here, you are coloring them with red. So basically, you are grouping pixels together. So what all things are happening here? You are detecting edges. Definitely, your network is detecting edges, complex edges, right? Not just vertical and horizontal, but at different orientations. So you are detecting boundaries of each objects, and then you are classifying whatever is there within those boundaries, right? So if it is a man, you are putting all people, all human beings with red color, all the vehicles with blue color. So what are the types of image segmentation? Again, whatever we discussed till now is semantic segmentation, which means we are just interested in the category to which a pixel belongs to. It does not care about individual instances. So basically, from this, I can say that all these are cars, but I cannot say this is car 1 and car 2 and car 3 and car 4 and so on, right? This instance segmentation, where we can clearly say that, okay, each vehicle is painted differently, each human being is painted differently. So I can say that, okay, this is car 1, this is car 2, this is people 1, people 2. I can mark them individually, right? So each instance get a different label here. But here, all the instances belonging to a same class gets an unique label. Is that clear? Okay. So moving on. Yeah, this is what we were discussing. Car 1 is yellow, car 2 is light blue, and so on. So basically, each vehicle gets an unique identifier. Now, panoptic segmentation is what is used in your self-driving cars, the video which we saw there. What does it do? It is a mixture of semantic as well as instance segmentation. So your instance segmentation, your semantic segmentation can be road. All the roads that the camera sees are classified as roads. You do not need to instantiate them, but you need to instantiate each of these vehicles in order to avoid collision. There can be vehicle 2 coming from left, vehicle 3 coming from right, and for your vehicle to make a decision, or some pedestrian crossing, pedestrian 1 crossing, pedestrian 2 about to cross, for your vehicle to make a decision, you need these instances and what kind of decision, given their positions, the position of each of these instances, what kind of decision your vehicle is going to take. Right? So this is the evolution of image segmentation. Again, like from classical stuffs to deep learning based approaches, and then transformer based approaches, foundation models. This is how things have evolved over the years. Again, so at the start of the session, someone had asked about how to enhance an X-ray image. So again, from classical literature, very simple enhancement or segmentation strategies, image thresholding. It is nothing but what you do here is, if you select a threshold intensity value, let's say 127, anything about 127 becomes white, anything below that becomes black. So the rightmost 2 images are thresholded, the leftmost are the left 2 images are the original images. In fact, the second one looks like a blurred version of the first image. So this has gone through some mean filtering. Any question? Is the value of kernel are fixed? Can give any value? Which collab? Someone is asking for collab. Okay, I will share it. Value of kernel in image processing literature, they were fixed. Today's world, we learn them. So what kind of thresholding we can do? There are some automatic methods that detect the optimal threshold. There can be adaptive threshold, which you basically, if your image is not, the contrast and brightness are not uniform across the entire image, a global thresholding won't work. You have to apply thresholding on small patches of the image, and you cover the entire image like that. You can get a value of the threshold that you need to use by plotting the histogram. We will see this in a very quick and short notebook session. So I am not like putting more time here. How to fix, coming to this, how to fix threshold using domain knowledge. Bones are bright and X-rays. Threshold separates bone from tissue. Look at the histograms. If this is the histogram, you have a clear threshold value here that you can take that will basically distinguish your object from the background. Let algorithms decide. Otsu's method, again, very popular thresholding method. It determines the threshold, optimal threshold automatically. And global versus local, as I was mentioning, if your brightness and contrast values are not like uniform, you need to apply them locally for a good thresholded image. So limitations, again, poor contrast image, noise and artifacts, uneven lighting, overlapping intensities, complex scenes. So these kind of handcrafted thresholding doesn't work, right? Next came region growing, again, like something which was very much used by doctors like as tools to assist them in diagnosing. So this is a CT scan, and then you want to segment out this region. So basically, you just use your mouse to click on a certain region, and then what it does is it grows, as the name suggests. The region grows. It starts from here. It checks the neighborhood pixels. If the neighborhood pixels are similar to this current pixel, it adds it to the region, and like that, it covers this entire portion. And finally, that becomes your thresholded image. Those locations becomes white, the rest becomes black. So you have a thresholded image. So again, this is another similar region growing technique. You have two spots marked here, and then the region grows accordingly, and then you have a segmented image kind of. So how that work? You start with seed points. So these are the seed points. You specifically mark them on the image, and seed acts as starting points for each region. Check neighborhood pixels. So basically this will check its neighborhood pixels. If the intensity values are similar, it will add. If yes, are you similar to the seed? If you are similar to the seed, you add it to the region or you stop growing. So similarity metric can be a choice of your metric: intensity value, color, texture, and other things. Is there any question? We can quickly take questions for 3 minutes, and then we will move on to the deep learning based approaches.
So, sir, if we understood correctly, so basically this thresholding and other augmentation type of things or growing of an image, that is done before we pass it on to the convolution layers, I guess, for the objective is better learning.
Yes, objective is better learning, but if you have decent amount of training data, this convolution layers, some of them might learn to threshold data as well. So in CNN world, there is no pre-processing as such. These are just motivations of how things evolved with years. So these are still used in classical region. Still works very well if you have this kind of thing and you do not have the budget to train a network. Neither do you have a training data. Just from a single image and marking this as your seed point, you can get a thresholded image.
Okay. But along with deep learning, one can also use this manual thresholding, because you showed some images where manual was anyway doing the best. The result of manual thresholding.
This one?
I think it was one of the previous one where you had marked the top left was manual. Yeah, I think top left was manual thresholding. There were 4 quadrants and top left was manual. Yeah, I think this top right. Yes, top right. Yeah. So as you see here, so basically the idea is to enhance and make the detection of the region of interest better.
Yes, I mean, you
Easier.
can do this as a pre-processing step if you want to. You can try out if you have less data as well. But then again, like the threshold value which you use here may not fit well for all the images in your training data set, right? So that has to be some adjustable pre-processing that you are doing. Maybe use this Otsu's method, which dynamically determines based on the image what is the threshold it should apply.
Okay, thanks.
So we will move on to image segmentation using deep learning. And again, like we discussed what is instance segmentation, semantic segmentation, and so basically your training image somewhat looks like this. Your cat is one class, so your training data has real images and then the mask. The mask is nothing but it associates each instance with some class. So your cat gets a color of 0. This grass and this trees on the background gets this pink color. I think not trees, but this is more of a mountain. Then the sky gets a blue color and this grass gets a green color. This is your training data. You train a network using this data, and at test time, if you're given an image of cows, your model should be able to say where in this region, like you will have a similar kind of image here coming from the network. At test time, classify each pixel of a new image, right? So semantic segmentation, again, like very simple idea is you have a sliding window, you take small patches and try to classify them. But then if I take this small patch here, like if you can see my pointer, this is all black. Without the entire global context, how do you say that this comes from the face of this is from the face of a cow? You cannot say, right? So how do we include context? So here the context is very important. So possibly you take a full image, you do a sliding window, overlapping segments, and then how do you model this? You basically do a sliding window kind of thing. You take small patches, overlapping patches, and you classify the center pixel, right? And if you do this entire thing for the entire image, you will get what each pixel corresponds to, right? A sliding window kind of a thing. But this is very inefficient because you will have to scan the entire image and do one classification, very costly to train also, and not using shared features which your CNNs are supposed to learn. So then let's go back to convolution again. Can we have a fully convolution layer? So when I say fully convolution layer, you are not doing any max pooling kind of thing. So spatial resolution is not decreasing, right? Let us go back here. Let us go back here. So here you are not using this fully connected layers. You are just using these convolution layers. You are not using any pooling as such. So basically the pooling layers are what is decreasing the spatial resolution. You are not using any pooling. You're just using fully convolution layer, few layers of them at the same spatial resolution, and the output is the mask. If you train like that, right? Yeah, if you train like that, see here, we are not using any pooling and we are just training a convolution. So finally, we can arrive at a mask which kind of is able to segment the original image, right? So this is a fully convolutional setup which works decently well, right? But then the very advantage of using pooling layers is you are shrinking the spatial resolution, which in turn reduces the computation overhead, right? The multiplication and addition operations. So this is again computationally very expensive, works fine, but computationally expensive and not something which, I mean, there are better ways to do that.
Sir, so just going to the previous slide, it mentions making predictions for pixels all at once.
Yes.
Yeah. So could you just elaborate this point again? I mean, with fully convolution all at once.
So these are feature maps, right? activation maps, right? So your final output is also an activation map, right? That activation map, the dimension of that activation map is your original image dimension. Both are same, right? What is your target here for segmentation? These are, if you have to, if let us forget all the background. Let us say that you have a binary segmentation kind of problem where your object is the cat and rest all is the background. I do not care about sky. I do not care about mountains and grasses. So this can be white. This can be black. The background, right? So you can do a pic, pixel level binary cross entropy here. At each pixel, you either predict if it is 1 or 0. You can do that, right? So output, you are predicting either 1 or 0. Output, you are predicting either 1 or 0. What can that be? If you multiply it by 255, 1 becomes the regions where it is 1, it becomes 255. The region which is 0 becomes 0. So you can get a similar kind of a, if it is trained properly, you will get a similar kind of a mask. Does that make sense?
Yeah, for the entire image all at once,
For
rather
that
than
entire image.
sliding that previously.
Yes, yes.
Fine, thank you.
So then people came, and we will discuss this encoder in our hands-on session. People came with encoder decoder kind of representation where like you definitely you do use those max pooling layers. And as you go deeper into the network, the spatial resolution decreases, but the features increase in size. And then you have a bottleneck layer. And then from here, you again start because in segmentation, your input image dimension and output image dimension should match. So you again do some, you do the opposite of max pooling. So basically from this, you are increasing in the spatial resolution, right? And finally, you are predicting this image. You are increasing till the original image dimensions are obtained. So this is called an encoder decoder kind of, where this half of the network is called encoder, the right half is decoder, and this is a layer.
So, sir, can we say this pooling and then padding, they are opposite of each other?
Pooling and padding, no. Padding is just to maintain, like padding after you apply a convolution kernel, it is just to maintain the exact spatial resolution. So, but yeah, I mean, not exactly opposite. So max pooling,
Functionally,
yeah, partially. But again, what you usually you use pooling with some stride, right? So the usual thing is the size drastically reduces without padding. It is just 1 or 2 pixels from the boundary that reduces. But with
so,
pooling,
I mean, functionally, because pooling tends to reduce the spatial dimension and padding, on the other hand, is enhancing that. Isn't that way?
yeah, but the scale at which pooling reduces, pooling will make, if you have a stride of 2, it will make this activation map into half. 224 cross 224 will become 112 cross 112. Padding might make it 222, 221 at max without padding. Or if you do padding, it can basically maintain the image resolution as well with same padding.
Thanks.
So yeah, so these networks, pooling is nothing but downsampling, and in your decoder, we are doing upsampling. But how to do upsampling? There are certain techniques. Nearest neighbors. So let's say your initial and a dummy 2 cross 2 input is 1, 2, 3, 4. You just replicate this and you get a 4 cross 4 output. So you are upsampling. This is called bed of nails because everything else is 0 and you just have one value here in each quadrant. So if you imagine like everything is flattened and then there are like nails coming out of each quadrant. So it is bed of nails. Then there is something called as max unpooling. So what it does is you remember. So this portion was where like max pooling happened. So from this input, you remember at which portion we took which portion was basically considered after max pooling. So in this first quadrant, you have this 5 as the maximum number. You store this value as 5 in the pooled activation map, but you also remember the position from where it came. So when you do max unpooling, you put this number 1 at the same position, right? If you see 2 to 6 came from here, so when I am doing max unpooling, I'm putting 2 here. This is more accurate when you have to preserve the location of the spatial location of some features, right? So we will go to applications of image segmentation. Again, like these have been taken from some sources. I have mentioned the sources here. This is a microscopic image and is trying to segment the nucleus. These are cells. Then this is like, this is again UNet. UNet is a segmentation network, encoder decoder based. We are going to cover that today in the hands-on session. Yeah, these are aerial maps. And then if you see, it has segmented the regions, like the green regions have been put as green, like green masks. And then you have the lake possibly in blue and the buildings, small buildings in red, the roads in black and so on. Something similar, this is on open source maps, OSM, OpenStreetMaps, OSMs, and it has segmented some grounds, possibly some arenas kind of thing. Again, coming to our favorite traffic scenarios, possibly also in self-driving cars, you are identifying the vehicles on the road and masking them. Not just vehicles, traffic lights and people as well. And there is a small animation of how this happens in real time. You see the person moving and all these masks are getting computed in real time. There are bounding boxes, so there is object detection also and segmentation happening at the same time. This is again in medical. These are your robotic arms, and then some sort of segmentation is happening on the robotic arm, and then how things are getting pulled. This is from NUS Mechatronics Lab. Yeah. Any questions? And then we'll move on to, let me open the chat window. I see 4 questions. What is the application of image cell? Please share the CNN Collab notebook again. So basically, yeah, coming to this question, will OpenCV work in PyTorch also? It is not like that. They are completely different libraries. So from OpenCV, you used to do some image manipulations, pre-processing. You load them into arrays or NumPy arrays using OpenCV library. You load images. You convert them into tensors, PyTorch tensors, and then use that to process in PyTorch. So these are different libraries for different users. Image segmentation can be considered as clustering. Yes, in a way, clustering similar pixels together, but then also ensuring that the spatial position is maintained. So basically, you maintain where in the image that particular pixel comes from. What is the application of image segmentation? I think we have covered quite a lot now. Are there any more questions? We will move on to the hands-on then.
Sir, just one last thing. You had mentioned, we can also visualize, like if we want to know what features have been learnt by these, all these CNN layers. And so how can we make sense of that? Means we want to know, because otherwise it's a black box. So we want to, for example, visualize what these CNN layers have learned, what features they have learned. So how do we visualize that? I think you mentioned it somewhere.
Yeah, so one thing you can do is, so finally, when you save the model, right? I think some model would have been saved, or is it still training? Yeah, it is still training for me. But once the model is saved, you will get the weights, right? And from the weights, you can extract, let's say, we are interested. Mostly the initial layers will make some sense. Later blocks It is a complex. It does a complex combination of the features which are being extracted in the initial block. So you take one of these filters, right? 3x3 out of these 32, you take one of these filters, and similar to the convolution thing we did, right? Here, pre-weight convolution, you use that as those weights, learned weights, as this array, right? And then you try to do the convolution and see what is the output image you are getting. Possibly you'll get some intuition on what kind of features that convolution kernel is helping us extract from the image. Does that make sense?
Yes, kind of. But have you included any such code in this notebook so we can?
I mean, no, but it can be done. It should be very straightforward to do that. And don't worry, even if you are unable to, after doing this exercise, even if the output features doesn't make sense, it does make sense to the network, and it is a very complex embedding dimensional space where possibly not everything we can visualize very well. But as long as our network is doing good on unseen data and on our validation and test data sets, we should be good. But yeah, to visualize, this is what we should be doing. I can see, like, I can make some change and share possibly something which is better, more intuitive to visualize.
Yeah, so that would be very nice, sir. Kindly.
Yeah, sure. So we will move on to UNet now. So again, as I was talking about this encoder decoder architecture, if you see the UNet architecture, I have linked the, I will share this notebook. Let me go through the theory part and then I'll share it. So as we were discussing the encoder decoder architecture, what the encoder does is it extracts features, but then as you move deeper into the encoder, the spatial resolution decreases. The unit original image was, or original architecture was applied to grayscale images where you have a single channel as the input, and that's why you have one here. And then if you see, and why the name unit, it can be visualized as the shape of U, right? And I just realized that becomes a song name. There is a song by that name. Anyways, so there is no padding applied here, and so there is some spatial resolution that is getting cut, but that is how UNet was designed. And you all the while you use 3x3 convolutions, and then as you go down, these are the max pool layers, right? And then you have up convolution as well, like from small spatial resolutions, you are trying to regenerate or trying to come back to the original spatial resolution at each of these stages. So you have up conv layer. You have conv 1x1 also, which comes from, where is that? Here, this one. This is the convolution, 1x1 convolution layer. Basically, what 1x1 will do is it will maintain the spatial resolution, but then you can change the number of filters, and that becomes your feature space. So any doubt? And then, of course, you are concatenating features at each abstraction. So this feature gets concatenated with this, so that like when we are downsampling in the encoder, we are not losing any important information as such. So they found out that this concatenation helped, and you can read the paper for more details. It is a decade-old paper, but works very well. Even in back in 2000, I think 2019 or 20, we had done an industrial project for Shell, and we had used this very network to do segmentation. That was for flare detection from chimneys. So this works very well. And the idea is very simple. Yeah. Any questions here? Okay. If there are none, I will share this link, and you can try it out. Yeah. Let me see if I can connect to a GPU. Yeah, I have got a GPU, thankfully. So let us run this few cells. So the data set that we are using today is the Oxford pet data set. It contains some 37 classes of dogs and cats with around 2000 images each. You have the segmentation mask. So as we were discussing, the entire background is treated as background. We don't have any class labels or labels for these pixels corresponding to this grass and the background. Just the object, and every other thing is background. So the objects are cats and dogs, and every other thing is background here. Right? We will download the data set. We will use the generators, and then there is a path, and we will do some visualization. Is everyone able to run? Sorry. First collab, okay. First collab. Is everyone able to run? So if you see this is the original image. And then this is the mask. This is the ground truth, basically. This is the annotation. If you multiply the original image with the mask, so this is a binary mask. You have everything in black as background and everything in white as foreground. If you multiply it, you are just able to segment out your object of interest. And after you have run this, can we please pause? I am going to discuss something important on how segmentation, the evaluation metric that is used for segmentation. So that is called as intersection over union. So basically, let's simply say that there is an object within a bounding box, but it works well for any complex shaped objects as well. And the intersection is how much the ground truth bounding box intersects with the predicted bounding box. So this is the intersection, the one here, and this is the union, right? So a good segmentation or a good even object detection algorithm should have a IOU score of 1. So basically, your actual bounding box and your predicted bounding box, or your actual segmentation mask and your predicted segmentation mask must be must be aligning well with each other. It should be a perfect alignment. Then only you will get an IOU score of 1. And that is what we try to maximize. Can you please tell the hashing technique in image segmentation? Hashing technique. What is this hashing technique? Can you please elaborate? If you are speaking, I am unable to hear you. Okay, I think I am unable to hear you. Okay. So this is the IOU computation. You can check how this is implemented. And this is the model which we are defining here. The same unit, not the same unit architecture per se, but a slightly smaller version. We are using 8 filters to start with. Here there were 64. Yeah. And here we are mentioning the callbacks. So basically your loss, training loss, validation loss, and mean IOU and validation IOU will be computed after each epoch of training. So let us start the training. Is everyone able to move to the training step? Can you please comment on the in the chat?
Other participants, you can also unmute yourself to answer the questions.
Yeah, if people have moved on to the training step, this training takes long. What we can do is we can go with, we can cover this image thresholding thing quickly. And I have some things to cover there, some interesting things. Yeah. Can we please have some response? Okay, okay, yeah, we'll wait for maybe 3 more responses. If people have been able to start the training. Okay. Any more? When the output is a binary hash code, okay, so we will move to this one, image thresholding. So let us again recall what thresholding is. Given a grayscale image, there can be thresholding on colored images as well, just that operations will be on the 3 RG and B channels. But given a grayscale image, if your intensity value is greater than a threshold, you set it to, you consider that as an object, you set it to white. 255 corresponds to white. And the rest becomes your background, black. Okay. So let us quickly run through this. But am I converting it to float? Image of data type, image. Where is this image? Okay. Okay. Do I have this? I think, okay, I understand this. I will have to upload this image. Give me a moment. I will upload this image. I need to provide this image as well, which I do not have at the moment. I think. Yeah, so I uploaded this image. I will share this image offline, or you can search for it on Google and download it and upload yourself. Okay, the issue was because of that. So you see, so in an 8-bit quantized image, you can have values from 0 to 255. I'm just using the half of that, 127 as the threshold value. So anything above the threshold value, I'm considering it as object, anything below as background. So if I do that hard thresholding, I get this kind of an image, right? Now let us understand the histogram. Histogram is nothing but, so since your intensity values can take from 0 to 255, you will have 256 bins, and each bin will contain a number which corresponds to the frequency. Frequency means how many times that intensity value has appeared in the image, right? So if you see, to compute the histogram, what I am doing is I am first initializing an array of length 256 with all zeros, and then depending on the pixel value, I am incrementing the number in this array by 1 at that particular position, right? So let us see. So this is how the histogram looks like. Why it looks like this? Let us see the original image. See, most of the pixels here are dark, right? So 0 corresponds to dark. So you have most of the concentration in the lower region, like lower intensity values, which means primarily like the most frequent intensities are dark. So finally, primarily you have black kind of, uh, the image is primarily has like more black regions, right? And then you have a small one, but a well spread one, which has like higher intensities, 100 to 150 until 200, and all the way up to 255 possibly. So that is nothing but these coins, right? So let's say we take a threshold value here. This corresponds to somewhere around possibly this will be 75, right? Let's say I take a threshold value of 75. So I should be able to distinguish all the whites from the black. Let's see how the image looks like. See, this looks so better than this, right? Almost everything inside the image has also been thresholded nicely, right? What if I select an intensity value here, like possibly this is 40? Let's see. You see, this is one of the challenges of using this kind of thresholding. You see this left portion, the brightness is not as, this black is not the same shade as the black on the right. That's why when I'm thresholding this using this kind of a, and that is the reason in the histogram we are seeing this kind of a dual peak nature. So this background is not very easily separable from the foreground with a small threshold value. So the optimal threshold is somewhere around 75, which is possibly the best we can do with this image. Questions?
Yeah, so could you explain that that overlap thing that you had showed, that ideally it should be 1. So do you discuss that aspect in terms of this particular thresholding?
Which overlap?
You just mentioned at the beginning of this particular discussion that I'm forgetting the name of that ratio, where you have that ideally it should be
Okay,
1.
IOU. This is
IOU,
from intersection over union.
Yeah.
So if you have to, let's say, for the sake of simplicity, let's say we are targeting an object detection problem, right? Where your ground truth are bounding boxes. We saw that in one slide. Let me go back there. Yeah, this, right? My model can predict a bounding box which is bigger, even though the entire car is contained within that, but a bigger bounding box is what my model predicts, right? What will be the intersection? The intersection will still be the region of the car, right? Intersection of this bounding box, which is the ground truth, versus what my model predicted, right? What will be
So
the
the actual
union?
versus actual car versus the box, that bounding box that the model predicts. Yeah.
Yes, yes. The intersection will be the actual car. Or let's say your model predicted something like this, some boundary. Is the laser pointer visible?
Yes, the laser point is visible.
Okay, okay. Let's say a bounding box, something like this is being predicted, right? I am hovering the laser pointer, which is covering the car partially, right? So what is the intersection? The partial region of the car that got covered by the bounding box. It is similar to this kind of an image, right? So this is your intersection. The union is the union of both the bounding boxes. This ratio will be lesser than 1. Intersection is, of course, lesser. The blue area is above in the numerator is lesser than the denominator. So this ratio is lesser than 1.
Less than 1.
Yeah. When does it become 1? When your bounding box from here, it predicts this, the exact one in the ground truth. Right? Because your intersection in that case will be the same. Your union in that case will be the same. So you are dividing two same things, you get 1 or close to 1. Does that make sense?
Yes. Yes, yes.
Okay. And I think the training, yeah, is progressing, and some epochs have completed, and you see, this is the validation step. So one image from the validation step. This is the mask that has been predicted. Not a good one yet, but it is able to do some decent segmentation. You see this mask, the model has predicted. You multiply it with the original image, you get some decent segmentation. This one is very nice, the last one. Right? So I think we have already exceeded time and we can stop here. I can take questions for another 5 minutes. And then, yeah, I think there are, so we share the link to the image. Image threshold link. This is the one.
Yeah, this is the one, yeah, the previous one. Okay.
Yes, yes, yes. Any other questions? Did we cover too many things? I just want a feedback for myself. Did we cover too many things in a very short period of time, or was it easy for people to follow?
No, sir, it was absolutely fine.
Okay.
Very
Okay.
nice session. Thank you.
Thank you. Yeah, if there are no questions, we can stop.
Well, I think so. There are some questions in the chat box.
Okay. Yeah, let me
Yeah, if you just please take a look.
If we okay, yeah. If we want to deploy model, we should go with pre-processing or keep it simple. I mean, it depends on. So first thing is, when you are deploying a model, you have to do the exact same step what you did in training. So you during training, if you used a pre-processing pipeline, that should be there in the deploy version as well. With CNNs, we usually get rid of these pre-processing steps like image enhancement and all, because the assumption is from a lot of data, the model learns to generalize well. Of course, if you do not have data, you do some pre-processing and then you possibly you use a smaller network to learn from features which are already processed. Does that answer your question?
Ms. Juhi, is your doubt correctly explained? Please, you can respond.
Sir, just one quick thing. Are you, I mean, could you guide with respect to neuroimaging data? And I don't know if that falls under computer vision domain exactly, but there was a task of, decoding the fMRI scans of the brain images into basically reconstructing the subjective experience of the subjects looking at the brain activity data. So does that fall under computer vision, or I just wanted to have a discuss on that. We can also do it separately if we have time.
Yeah, I would want to know more about this before commenting personally.
Okay.
Hello.
Could you please share any contact coordinates on which we maybe write to you on email? Or
Yeah, sure. You can send me an email. What I can do is I can get in touch with my friend who does a lot of this medical image and signal processing stuffs, and he collaborates with a lot of doctors for this. So yeah, I can get some inputs from him and get back to you.
Sir, am
all
I,
right. Thank you. Right to you.
Thank you.
sir, am I audible?
Yes.
Sir, I wanted to know that if we are deploying a model, so
Mhm.
we are going to have our weights and biases from the training exams. So doing a lot of pre-processing or doing less pre-processing, will that affect during deployment?
See, while we train a model, we do some augmentation. Leave aside the pre-processing steps, right? We do some augmentation. That augmentation might be basically randomly cropping your image. I was mentioning that dog image, right?
Yes, sir.
We might take a random crop, horizontal, some flips we might do, and all those kind of pre-processing steps. But when you do, so this is used for CNN training, just for the model to see more images and generalize better, right? This is the only objective of this kind of pre-processing. We do not use these pre-processing. We do not use augmentation at test time. Okay,
Yes, sir.
so that is something which we do not do. Now, if you have a pipeline which applies a constant pre-processing, and then your model has been explicitly trained on those pre-processed images, like let's say you are getting colored images and you are training a model with a contrast enhanced grayscale version of the colored images, then this pipeline must be there in your evaluation or in your deployed model also. So any image you get, you first convert it into grayscale and then do some contrast enhancement and then put it into a model. Because if something has been trained on single channel data, first of all, it don't accept a colored image, right? 3-channel images. And even if you do something, you have to replicate the pipeline which the model saw in the training setup. Does that answer your question?
Yes, sir. Got it.
Okay.
And so one more question about the hashing technique. Like you gave the example of the CNN thing, but
Mhm.
earlier I have attended one of the lectures. So there someone told me like there's a process of hashing and image segmentation where they use binary numbers 0 or 1 for representation of the hashes. So when we are exclusively using deep learning models, so training during back propagation using gradient descent, that becomes difficult because of the presence of ones and zeros because they take it as impulses. So there the professor told me that there the technique of backprop is a little different. So I was asking if you could tell me something about that.
Okay, I am not aware of exactly what it means by this hashing, but then one thing that I can tell you here is, let me go to the slide. Yeah. So here, if you see, we are using but that model, yeah, we are using sigmoid activation function, right? Sigmoid can accept values between 0 and 1, and it is a perfectly differentiable function, right?
Yes, sir.
So with this kind of masking strategy, this should
Sir,
work as.
your slide is not visible if you are sharing something.
Oh, okay. I'm sorry. Yeah, let me share my screen. Yeah, is it visible?
No, sir, not.
Uh, no. Okay. My screen is not visible. Let me. Okay. Oh, some issue with possibly. Okay. Somehow I am unable to share my screen. I am not sure what went wrong. But can you open the unit notebook
Okay,
at
sir.
your end and just go to the model part where the unit architecture is defined?
Yes, sir.
Yeah.
Yes, sir. I look at it.
Yes. So basically, if you see this activation, outputs equals to const 2D, you do a 1+1 convolution, and then activation is sigmoid, right? So
Yes, sir.
sigmoid is a perfectly differentiable function, and the values can go from 0 to 1. So it is a bounded function as well.
Hmm.
So we can use this in backpropagation perfectly well. Does that answer your question?
Okay, we'll have to customly define it to be used.
I mean, yes.
Okay. So, so there are other functions as well, like with the mark 10. Yes, and sigmoid is also used in a few places. Okay, so like changing the function which is to be used during the backstop, that is the NVDR.
Yeah, I mean, you have to, anything you are using, you have to ensure that it is differentiable. There are ways where if that nonlinearity breaks, people do some approximation. I'm not sure if in segmentation it is required to, but yeah, maybe I might not be aware of that. Yeah. Yes.
Thank you, sir.
Sure. Are there any other questions? Okay, I think we will end then. Yeah, thank you so much for your time.
Thank you very
Yes,
much,
sir.
sir, for a great session.
Hello, sir. I'm audible?
Yes.
Yes, sir. Okay, so thanks a lot, sir. We understand you taking time from your busy schedule, and it was an amazing session. I mean, all of these things have been discussed before, but getting an overview and the idea for choosing the specific field, I think all the participants have understood really well today. So thank you for your insights and guidance. And we'll really be looking if we can have you in our upcoming sessions also for the same. It was really great. Thank you, sir.
Sure, thank you so much. I'd be glad to be
Yeah,
part.
Ishita, would Prantik sir take the afternoon session also?
No, ma'am. For today,
Acha.
it's different.
All right. Thank you. Thank you, sir.
Thank you.
Thank you, sir. You can leave the meeting now.